Theodora. Theodora commence juste son travail de doctorat. Elle vient de passer, enfin, elle a commencé depuis 2 mois. Theodora MAVROGIANNI, pardon. Elle réalise son travail de doctorat entre le C2RMF, le groupe organique, et l'IRCP. Elle est financée par Chimie Paris-Tech, Université PSL. Et aujourd'hui, elle nous parle des matières noires utilisées en usine. Theodora, thank you. You have 5 minutes.
Alors, this one?
Yes.
Okay. C'est ça. Okay.
So, hello everyone, my name is Theodora MAVROGIANNI and I'm a PhD student that just started now in October. And today I will make a brief introduction of my thesis, which is called The Black Matters of Ancient Egypt from Molecules to Recipes, where I will work under the supervision of my directors, Agnès LATTUATI-DERIEX here at the C2RMF and Professor Laurent BINET at the PCMTAS at Chimie Paris-Tech. So first, before jumping into the objective of this thesis, I would like to make a general background. So thinking about ancient Egypt, the first thing that is, of course, the mummies. So we all know that the mummification was a sophisticated method to preserve the dead body, and the embalming black matter is generally known as black matter in general. And little information is known about this black matter since the ancient Egyptians didn't leave any written records, but elaborate research has shown that the black matter is the result of a complex mixture of inorganic and organic materials and from various sources. For example, plant gums, vegetal resins, animal fats, pitches, and bitumen. And all of these substances have specific molecular markers, which are mostly identified by analytical techniques coupled with mass spectrometry. So I would like to give a special focus on the bitumen, which is a component of petroleum and was increasingly used at the New Kingdom era and onwards. And it has two very important and interesting components, the carbonation radicals and vanadil porphyrins. Now the vanadil porphyrins in general structure is shown on the upper corner. And what is interesting about them is that both of them have unpaired electrons, and they can serve as paramagnetic species. And we can use that to our advantage since they can serve as internal paramagnetic probes. So we can monitor them and identify them with electron paramagnetic resonance techniques, and which is very powerful technique. And most importantly, it's non-destructive. And we all know how important this is when dealing with precious archaeological samples. So when dealing in general with the artifacts, the same cultural, geographical, and historical questions come to mind. And the ultimate goal of this thesis would be, of course, to try to answer them. So the questions are related to what materials were used, where did they come from, and how they were manipulated in the manufacturing process. So, of course, our starting point starts with all the information gathered by Océane, who was a former PhD student, and her thesis demonstrated the importance of combining analytical techniques and mass spectrometry with ion beam analysis and electron paramagnetic resonance techniques to study and to identify the raw materials used for these black matters. So now we would like to take it a step further and try to study the black matter, of course, with all the analytical techniques that Océane used, and additional ones that will allow us to have a wider range of organic and organometallic identification, for example, high-resolution mass spectrometry. And the second objective would be to try to study the interactions of these raw components by trying to mimic the ancient recipes, so by mixing reference materials of our own in various proportions and heat them up in various temperatures and heating duration times, and try to see how the molecular fingerprint of these raw materials will evolve throughout this manufacturing process. So in order to achieve those two objectives, first we will have to do the speciation of the black matters and then study the interactions. So I will try to spend half the time at the C2RMF, where I will do low resolution single quadrupole GCMS, and at CIMI Paritech at the PCMTAS team, I will do the electron paramagnetic resonance techniques. And thanks to the collaborations that we will have access to high resolution analytical mass spectrometry and analytical techniques. So I will also spend some time at the Université de Lorraine and at ESPCI, where I will do magnetophemes and high resolution liquid chromatography, where we can study higher molecular weight compounds, such as proteins and carbohydrates. So that was very brief, but thankfully next time I will have some interesting results for you all, and thank you for your attention.
We have time for one question. Est-ce qu'il y a une question dans la salle ou sur le Teams?
Ça n'a pas marché.
Ah, ça n'a pas marché. Oh no.
Oups, dommage. Désolé.
I have one question, Theodora, conservation question. Do you see at the end of your work, all of the work of identification of the specific components could help the conservator to adapt the conservation treatment or the conservation conditions?
Of course, I focus more on the historical and the cultural meaning of the work, but I'm sure that the more we get to know, the better for the conservators. So of course we can identify some raw materials, but by studying the interactions, we can see how they evolve over time. So maybe some of the components will interact with each other, they will polymerize and change and continue on doing end up as something else. So I think that for the conservators, it will be very important to see what we have now and not only what we begin with, so that with this in mind, you can proceed accordingly for the conservation process.
Okay.
I assume I'm not conservator.
Thank you.
Thank you so much.
Une autre question dernière, un petit peu juste. Thank you.
Thank you so
Theodora.
much.